Okay, so just to finish our discussion, we defined the Ricci contraction C of t of a 0,4 tensor t, given by the 0,2 tensor, which is the trace of the linear map, which takes a vector and plugs that vector into the first component of the tensor. The two inputs of the Ricci contraction tensor are the second and fourth inputs of our tensor t, and then the third input is basically the input of the covector, which turns this t of z x dot y into a covector. We take the sharp map, that gives us a vector. Okay, so then we get a linear map which sends this vector z to this vector sharp t of z x dot y. We take the trace of that linear map, that gives us a real number. Again, we discussed the definition of the trace, which there are many different ways to define it. You can do it in coordinates, and then it's just the trace of the matrix representation of the linear map, which is independent. It's invariant under orthogonal transformations, so it's independent of the choice of coordinate basis. And then also, we can define it as the sum of the eigenvalues of the linear map, but there was this other definition which I mentioned, which was that we can find an isomorphism between endomorphisms on V and V tensor V dual, which sends V tensor omega to the linear map, which sends a vector Q to omega of Q V. And then this is an isomorphism. Then we can take our endomorphism here. We can take a linear map and send it to V tensor V star, and then the trace map is just defined by literally contracting. It's defined on the basis of V tensor V dual by contracting V tensor omega and sending V tensor omega to omega of V. Okay, so this is our Ricci contraction, and then if we take the Ricci contraction of the Riemannian curvature tensor, we get what's called the Ricci curvature tensor. It's important to note that if T is a curvature like 0,4 tensor, so aka it satisfies the first Bianchi identity, then our Ricci contraction will be symmetric. Okay, so C of T of xy is equal to C of T of yx. Okay, now we're going to define the trace of a 0,2 tensor. Okay, this is a bit simpler definition. So we take a 0,2 tensor, and we can build a linear map which takes a vector x to the sharp of the one form t of x comma dot. Okay, so again, similar construction. We've defined this linear map which takes a vector x to the vector which is the sharp of the covector given by t of x comma dot. Okay, then we take the trace of this linear map the way we've just described. We take the trace of this linear map, and this gives us the trace of a 0,2 tensor. Now, if we take the trace of the Ricci curvature tensor, okay, so take the trace of the Ricci curvature tensor, we get what's called the scalar curvature of the Riemannian manifold. Okay. All right, and then this is another final important section here, which is the coordinate forms. Okay, so just recognize that this Ricci contraction of a 0,4 tensor is essentially going to contract the second and fourth indices, which is equivalent to contracting the first and third indices. Okay, so you can just see this formula here. I'll zoom in on it. Okay, so this is the Ricci contraction of a 0,4 tensor in coordinates where G superscript PQ is defined as above. Okay, so G star is this dual metric which we discussed previously, and then these V superscript P and V superscript Q's are a basis of V dual. So go ahead and take a moment and recall what is the definition of this G star if you forgot. Okay, and then the trace of a 0,2 tensor, the trace of a 0,2 tensor is defined as this contraction here. So we just contract the two indices against the metric. Okay. All right, and it's important to note that in fact this trace is the same as the inner product of the tensor with the metric. Okay, so the metric is a 0,2 tensor, right? Takes in two vector fields, outputs a real number. So, and it's bilinear, or Yeah. So the metric is a 0, 2 tensor. So is this tensor T that we're taking the trace of. Turns out the trace is literally just the inner product of these 0, 2 tensors T with the metric G, right? Where this inner product on the tensor bundle we defined previously, okay? All right, so that's going to be, and we're going to come back to this soon enough for part B, because that is not all of lecture 8. That is only half of lecture 8.